motion lab. In the motion lab, we are going to talk about linear and curvilinear motion. We will talk about the lab. We will have a small discussion about lab view that will not be a part of this recording. It will be part of the lab recording. And we will talk about calibration. That also will be a part of the lab recording. So you want to make sure you watch the lab recording. Let's run most of them to understand and learn how to do the lab. Okay, motion. To describe the motion of an object, we must first find its position at a certain time. Whenever we find the motion of position of a specific particle, a specific object at different times, we can find the displacement by subtracting the motion at an initial time from the motion at a current time. So initial position minus or the current position minus the initial position is going to give us the displacement. And using the displacement, we can find the velocity and acceleration. Velocity is defined as the displacement, the derivative of the displacement with respect to time, and acceleration is defined as derivative of velocity with respect to time, which means that it is the second derivative of displacement with respect to time squared. Using these, we can get to the big four equations of linear motion. The first one tells us that displacement is equal to 1/2 of initial velocity plus the current velocity multiplied by time. The second equation relates the velocity to acceleration. The current velocity is equal to the initial velocity plus acceleration multiplied by time. And the third one relates the displacement to acceleration. All of these are just integrals of the definitions of acceleration and velocity. So the third one is going to tell us the displacement is equal to the initial displacement plus the initial velocity multiplied by the time plus 1/2 linear acceleration multiplied by time squared. Again, we have derived these just based on the uh, definitions. We have integrated the definitions, and these are the equations that we get to by just integrating. So all of this is going to help us measure the displacement, velocity, and the acceleration. We're going to talk about the fourth equation later on. So we can have the same arguments, same definitions for a rotational motion. A rotational motion essentially refers to the motion of the particles of a rigid body that are rotating around a center, right, on a specific plane. We have different types of motion. We have translational motion when the particles of a rigid body move along the path, all of them at the same rate. Essentially, all of the particles translate at the same rate from one location to another location. Rotational motion, as I said earlier, is the motion rotating around the fixed axis. All of the particles of the rigid body are rotating around the fixed axis. So in general, motion can be rotational and translational. Let's see how we can analyze and formulate the rotational motion. Let's think of a particle that is moving on the path S around the center O. The radius, the distance between the particle and the center O is R, and at each time the radius has the angle theta. So for this type of motion, we can define the angular displacement and the rate of change of theta, and we can relate the theta to the path taken, this path, and the radius of our rotating particle. This is using just the arc length equation. The arc length, which is this path, is always equal to radius multiplied by theta, which means that theta at each time is going to be equal to S divided by R. Displacement, angular displacement, is going to be equal to linear displacement, this path that's taken, divided by the radius. Okay, so using this definition and the previous definitions that we had for velocity, we can define the angular velocity as a derivative of theta with respect to time, and we can define the angular acceleration as a derivative of omega, which is our angular velocity with respect to time, or the second derivative of theta with respect to time squared. Okay, so we can a couple of principal equations for the angular motion as well. Theta, angular displacement, is going to be equal to initial displacement plus the initial angular velocity multiplied by the current time plus 1/2 angular acceleration time squared. So the fourth equation that we didn't mention is the relationship between the rotation and the linear displacement. We did talk about the arc length equation. Arc length or path a particle takes from one point to another point is equal to the radius multiplied by the angular displacement. So linear displacement is equal to the radius multiplied by the angular displacement. So based on this definition, we can relate the angular velocity and the linear velocity to each other. Angular velocity is derivative of path with respect to time. Angular linear velocity is derivative of path with respect to time. Angular velocity is derivative of angular displacement with respect to time, which means that our linear velocity is equal to radius multiplied by the angular velocity. We can have the same definition for tangential velocity, specifically just tangential velocity, which is equal to the derivative of velocity with respect to time, which means that it is going to be equal to the radius multiplied by the angular velocity. So tangential velocity is going to be equal to radius multiplied by the angular velocity. You have to keep in mind that there is a normal component to this acceleration, and that is the centrifugal acceleration, which is v squared divided by r. We don't really discuss that here. That is not something you want to use in your calculations and your analysis. So we are only focused on the tangential velocity acceleration and its relationship with angular acceleration, which is equal to r multiplied by the angular acceleration. Okay, so to understand the displacement and the relationship between the rotational movement and the linear movement, we have to make some measurements. We have to measure the displacement. We have to convert this displacement to velocity and acceleration. And using this equation, the two, we can check the relationship, we can check the measurements and everything. We can do the same thing for the rotational movement and relate the angular displacement to acceleration like this. And eventually, we are going to relate the two accelerations to each other. The goals of this experiment is to learn uh, how to make measurements for motion using an ultrasonic positional proximity sensor and using an optical decoder. Optical decoder is used for the rotational motion. Ultrasonic position or the proximity sensor is used for the linear motion measurement. And eventually, we are going to learn how to determine acceleration from two different methods. Linear acceleration specifically from two different methods. One from directly from the linear uh, movement measurement, motion measurement, and indirectly from rotational movement measurements. And you do have to do a lot of carefully here, and we're going to discuss that when we are demoing the lab. Okay, so let's see how the lab is going to look like. This is the schematic of your lab. We are going to have a disk that is rotating, and we are going to have an optical decoder on this disk installed that is going to measure the angle based on a base angle. We're going to define a zero angle, and based on that, it's going to tell us what the angle is, the angular position is at each time. And this rotating disk is connected to a falling mass through a pulley system. And we are going to measure the positions of this falling mass using an ultrasonic sensor that is this. The ultrasonic sensor that is installed just behind it, beneath it, has to be directly beneath the falling mass. Okay, so using this, we are going to measure the linear displacement at each time. Using this, we are going to measure the angular displacement at each time. And using this information, we can find the angular velocity of the angular acceleration of the disk and the linear acceleration of the falling mass. And these two are related to each other. Uh, Force balance. You can relate them to each other using the force balance on the hanging mass. So it is pushed on by the weight of the mass and pushed back up by the rotation of this desk. Then just to set these two equal to each other and say equal to mass times acceleration. That should give you an acceleration as a function of angular velocity. And you can find the linear acceleration just by using the falling mass using this equation. Okay, so we have an ultrasonic transducer, we have an optical decoder. Let's learn how these two work. An ultrasonic transducer working principle is pretty simple. You are going to generate uh, some sort of a wave, and this wave is going to hit your object. Your object is going to reflect the wave back, which is going to be received by the ultrasonic transducer. And the ultrasonic transducer is going to know the time it has taken the wave to be reflected to it, and it also knows the velocity of the wave. Okay, so using this equation, we have the velocity, we have the time. It is going to take, I guess, double the amount of time, double the amount of distance, I'm sorry, to go to this object and come back. We are essentially interested in just half of that value, which means that you have to divide it by 1/2. So your distance is 1/2 of the velocity of the wave multiplied by the time it takes to go from for a wave to go from the ultrasonic transducer to the object and go back to the ultrasonic transducer. Okay, we usually generate waves that are larger at 20 kilohertz frequency. As I said, they bounce back when encountering an obstacle, and we are interested in measuring the time of reflection, how long it has taken the wave to come back to the transducer. Okay. One thing you need to do, this is where the calibration comes into place. You need to make sure that you tell your software, your LabVIEW software. Again, we're going to learn how to write the LabVIEW code later on, but you have to tell your LabVIEW software uh, what each voltage change means in terms of the distance. You essentially have to have to make a couple of measurements and measure the distance from a base point. That base point, it can be the ground, it can be this the location of the ultrasonic transducer, and then for all of those, the reading you're going to see is not going to be a distance, it's going to be a voltage. So essentially, this ultrasonic transducer, upon receiving a reflected wave, it's the voltage in it is going to change, and that voltage will be read by a computer. So you are going to have a couple of voltages, you are going to have a couple of distances. Using those, you can relate the voltage to the distance. We're going to see all of those later in the lecture notes. You don't really need to know, in the lab recording, you don't really need to know how to do any of this right now when you're watching the lecture. Yeah, we did talk about how to convert voltage to distance. We just need to make a couple of measurements. So the software doesn't automatically this calculation. Doesn't automatically do this calculation for us. We just need to use the voltage instead of velocity at time to find a correlation between voltage and the radius. Okay, so let's talk about the optical decoder. The optical decoder is an electromagnetic device that converts the mechanical position of a rotational part to electrical signal. Means that it converts the angular position, angular displacement to digital signal. But the software we have does convert this digital signals or electric potential back to angle. So we don't really need to do calibration for this part of the experiment. But essentially, its working principle is using a light and passing the light through a grated, through a uh, black and white disc like this. So there will be location where the light that will pass the light source to get to the light detector, like right here, and these black areas is not going to let the light pass. Based on this, your sensor is gonna know that you are moving, and it's gonna know the rate of moving, how fast or slow you are moving. But there's one thing we need to make sure to know. We need to know so the software can decode this, convert this potential differences back to angle. We need to do the number of the black areas that are color black. So the software has to know what a 360 degrees rotation equal to. What is it equal to? So the number of black dots is black areas is important in our analysis. And for you guys, the number is 720. So we have 720 black dots on our disk. You are not going to really see that this is beneath the disk, behind the disk. You are not going to see these black dots. But if you are very interested, you can let me know. I can show you with greater details how the sensor works. Okay, this is it for the lab. So the idea is you are going to do a couple of measurements uh, for three different weights. Specifically, make sure to read through the lab reports. And for these three different weights, you are going to measure the linear displacement at any time, at a couple of different times, and the angular displacement a couple of different times. Based on this, you can measure the angular velocity, angular acceleration specifically, and linear acceleration, and we can find the relationship between these two, and we can see how accurate our measurements have been. That is it for today's lecture. Thank you for joining us, and enjoy the rest of the day.